Hello dear students, and welcome back to Rubber Duck Physics. At the end of the last video, number 4, we asked the question. Two astronauts are moving, relative to each other, both carrying identical clocks. Since motion affects time, could one astronaut's clock tick slower than the others? This is one of the strangest consequences of Einstein's relativity. Today, we'll explore the idea of time dilation, how motion affects the passage of time itself. Einstein's postulates led to a bizarre prediction. If you measure the ticking of a moving clock, it will appear to run slower than a clock at rest. This is called time dilation. Moving clocks tick more slowly when observed from another frame. The word dilation means stretching or extending. To help visualize it, imagine a metronome, ticking steadily at a fixed rate. If you watch it from the front, the motion looks perfectly even, but if the metronome is moving sideways while ticking, the beats seem stretched out. Time dilation works similarly. Motion changes how different observers measure the duration between two events. This metronome example is of course not the case where time dilation can be shown to happen, but an analogy to imagine it. Let's now consider two real observers, both moving relative to each other. Let's first look at one moving observer and one stationary observer. The yellow duck stays on Earth, sitting next to a stopwatch. The blue duck is flying past in a spaceship carrying an identical stopwatch. According to the yellow duck, the blue duck's stopwatch is ticking slower than normal. This is the basic effect of time dilation. A moving clock appears to run slow compared to a stationary one. But now let's change the setup. Instead of one duck staying still, both ducks are now in spaceships, flying past each other in opposite directions. Now, the yellow duck sees the blue duck's clock ticking slower. But if motion is relative, and if the laws of physics are the same in all inertial frames, how do we decide which one is experiencing slower time? We can only conclude that at the same time, the blue duck will see the yellow duck moving relative to it and therefore its clock ticking slower. Each duck sees the other's stopwatch running slow. This happens because in special relativity, time stretches when viewed from another frame of reference. And, by the way, if we go back to the first example, the blue duck in the spaceship will see the yellow duck as moving together with Earth, and therefore even in this case, the blue duck will confirm that the other observer, the yellow duck's clock, runs slower. This is what makes time dilation so unintuitive. There is no universal agreement on which clock is truly correct. Let's put the idea into an equation. The time dilation formula can actually be derived from first principles. It comes from a thought experiment featuring a light clock, where we analyze how light bounces between two pairs of mirrors, one at rest and one in motion. Using the Pythagorean theorem and Einstein's postulate that the speed of light is the same in all frames, we can prove this equation mathematically. We won't go through the full derivation here, but it's important to know that this equation is not just a rule we state, it follows logically from Einstein's principles. The time interval observed from a moving frame is given by time interval equals gamma times proper time. And gamma, the Lorentz factor, as you already know, is given by 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. We first saw this in video 3. It tells us how much time is stretched, depending on velocity. The faster you move, the larger gamma gets, and the more time slows down. But what exactly is proper time in this equation? Proper time is the shortest possible time interval between two events, measured in the frame where the clock is at rest. If you are holding a stopwatch, the time you measure is always proper time. Someone watching you from a moving train or spaceship will measure a longer interval. Proper time is always the smallest possible time interval between two events. Now, here is an important detail. If you are moving at very high speed, do you feel time slowing down? No, you experience time normally. Your heart beats at the same rate. Your thoughts flow as usual. It's only when comparing two clocks in different reference frames that we see time dilation. This is a real effect, not just a change in human perception. If living beings could already travel at speeds comparable to the speed of light, even the rate of their biological processes, like aging or the developing of a disease, would slow down viewed by an observer moving relative to them. Although not by such means, time dilation has been experimentally measured many times. Muons created in the upper atmosphere should decay before reaching Earth, but because of the dilation, they last longer and reach the surface. Atomic clocks flown on airplanes tick slower than identical clocks left behind on Earth. Since these experiments also confirm another effect covered in the next video, we'll revisit them then. Now let's take our equation and ask a question following from it. We have seen that moving clocks tick slower given by time interval equals gamma times proper time. And we know that gamma appears in both equations of the Lorentz transformations, also in the other one governing the transformation of position between reference frames. If time is stretched by gamma, what about space? Could distance also be affected by motion? Imagine a spaceship moving past Earth at nearly the speed of light. Observers on Earth see the spaceship's clocks ticking slowly. But from the astronaut's perspective, it's Earth that is moving. So what do they see? If time is slower for moving observers, could space itself also be different for them? That's what we'll explore in the next video. Before we go, if you would like one-on-one tutoring in IBDP physics, A-level physics or mathematics, or AP physics, I also provide online lessons. You can find my email address in the channel data of the Rubber Duck Physics YouTube channel. It's only visible if you view it on a computer browser, not in the app. If you would like extra help with relativity or any other topic, feel free to reach out. Thank you for watching Rubber Duck Physics. See you next time.